Well, today, as I said, we have Marty Mulvihill from the University of California at Berkeley. Marty received his PhD from UC Berkeley in 2009 in synthetic chemistry, and he has quite a long and interesting bio, but I'm just going to pick some of the highlights this afternoon. At UC Berkeley, he founded the Green Chemistry and Sustainable Design Seminar, a graduate student-organized seminar series which is now beginning its 4th year. For his work in bringing green chemistry research and education to the Department of Chemistry, Marty was awarded the 2009 Benjamin P. Bussert, I hope I said that right, Memorial Award. He is currently the executive director of the Berkeley Center for Green Chemistry and a postdoctoral researcher in both public health and environmental engineering. He's been developing new green chemistry laboratory exercises for the introductory chemistry curriculum, and he's also been coordinating and teaching a new interdisciplinary graduate class in green chemistry. To support the development of new materials, Marty uses green chemistry to designing inherently safer chemicals. In particular, he focuses on the connection between nanoparticles, chemical characteristics, and their functional properties and fate in the environment, and that's really what he's going to be talking about today. So thank you so much, Marty. Welcome to our webinar, and please proceed.
Thank you very much, Lynn. It's a pleasure to be here this afternoon, and it's a lot of fun for me to share my research in this way over the web with folks. This is one of my first webinars, and it's interesting to be in my own office and not see all of you out there. But I look forward to your questions at the end nonetheless. So what I'm going to tell you about today is, in fact, what I've been thinking about in terms of my own research. So as a graduate student here at UC Berkeley and then a postdoc at the National Labs, I was really interested in the life cycle of nanotechnology. So how to make nanotechnology that presents benefits in terms of its operation, its function, and is also, from a life cycle perspective, green, such that it doesn't have any unnecessary impacts on human health or the environment. So I'll tell you a little bit about both my graduate and my postdoctoral work today. So just to get started, I always like to place green chemistry within the context of sustainability, which I think is the very broad work that's being done by many people in many different disciplines, such that we can meet the needs of the future while still meeting our own needs today. Green chemistry and green nanoscience, by extension, in my opinion, is what that looks like at the molecular level or at the nano level. So how do we make things in the lab that help promote sustainability? And I think that there are actually a lot of natural connections between green chemistry and nanotechnology. And the two things that I pull out actually in the citation here on the bottom is a recent review article that I wrote with Paul Anastas and Evan Beach and Julie Zimmerman. And one of the case studies we use is the green chemistry and what it can learn from nanotechnology and what it has in similar to nanotechnology. I think two of the trends that come up are, first, this notion of dematerialization. Nanoscience is controlling things at a very small level such that you can actually use less material. So use less metal for your catalysis than you used to do when you were using bulk metals. That's the promise. And when it works well, when it meets both of those things, it meets the promise of both nanotechnology and green chemistry. And then transmaterialization, and that's really thinking about, from a life cycle view, where are your products coming from and where are they ending up in the environment? And I'm going to talk about especially the latter half of that, where they end up in the environment and how we can use the design of nanoparticles to help dictate and help understand what some of the concerns may be and how we can design away from those concerns. So the other thing that I think is we have in common between nanotechnology and green chemistry is that they're both horizontal technologies. They're really approaches rather than a technology in and of themselves. nanotechnology or green chemistry can both be used to help provide clean water, to provide clean energy. There's a lot of health applications coming out for nanotechnology. Food, nanotechnology-enabled packaging so that you know when your food's gone bad, sensors, things like that. So both nanotechnology and green chemistry are really horizontal in the fact that they cut across a lot of traditional fields, and they're really, in a lot of ways, more of an approach rather than an end product. And in fact, it's interesting to look at some of the economic projections for both nanoscience and green chemistry. And if you take a closer look at these sometimes very large numbers for what the impact of nanotechnology is on the economic value chain, you actually see that when you're looking at the nanomaterials themselves, the percent of value that they actually contribute is usually less than 1%. The value is really coming from the nano intermediates, so the things that go into your final product that were made using nanotechnology, and the overwhelming percent, greater than 85% of the value when you estimate the value of nanotechnology in the marketplace is actually coming from the overall value of nano-enabled products. So it's the things at the top that you're really making and selling and providing with nanotechnology or green chemistry. And that nanotechnology and green chemistry are the way you get there. So if we think about what this would look like, and we want both green processes, so making nanoparticles and other things in a green fashion, and then of course we want green products. And by green products, what I'm thinking about are the applications, so things that advance clean water, clean energy, but also things that don't have unintended consequences, that don't introduce new toxicity or new environmental harm. So I'll talk about both of those. Just to give you an idea of where we are, this is a great review article that actually comes out of Julie Zimmerman's lab at Yale, taking a look at what room do we have for improvement in the nanotechnology process area. And you can see from these numbers, these E factors, which is the massive byproduct over the massive desired product, that we have a long way to go in nanotechnology. This is not yet dematerialization. You can see that, especially when you take into account purification steps to isolate pure single-size nanoparticles, you often end up using a lot of solvents and a lot of auxiliaries in the process of making a lot of these particles. So I think we can learn a lot from the 12 Principles of Green Chemistry, and actually this is an excellent review article by Jim Hutchinson, who's certainly one of the leaders and fathers in the area of greener nanoscience. And in this review article, he really translates the traditional 12 Principles of Green Chemistry into the design of greener nanomaterials. And as you see, most of these have to do with energy efficient processes, materials and process efficiency and safety, and reducing waste and environmental impact. A lot of that would add to getting down that E factor, to making nanoparticles in a greener way. And in the examples I'll tell you about today, I will lay to bear exactly how green and not green they are, because as with anything, it's all about moving in the right direction. I want to be greener than the numbers you just saw here, but I'm not yet to a perfect E factor. I think that's one of the things I would like to see in this area in particular. I think it would help both nanoscience and green chemistry to just be more honest about what our wastes are, where they're coming from, and what their impacts may be. So when it comes to greener and safer products, you have two concerns, like I mentioned earlier. The first is you want the materials to be used for something that's beneficial for society, that's really adding to some of these water or energy challenges. But then in the lower handle, what you see here is a cartoon rendering of a nanoparticle interacting with tissues and with the cell. And we want to know that these interactions are benign and not dangerous. And in fact, along those lines, there's been a lot of research lately, and for good reason, into what the potential toxicity and impacts of nanomaterials are. And I like to bring up the point, and a lot of people recognize this already, that nanotechnology is not inherently safe or inherently dangerous. In fact, these are some of the ways that we should consider, and this is an excellent review article by Andre Nell down at UCLA, talking about what are the modes of biological interaction with nanoparticles. And they're things that we understand, and as chemists and as nanoscientists, we really need to think about which of these might be at play in any system that we're making. And the one that I'll actually talk about today is down here, the dissolution and passivation. A lot of the impacts of nanoparticles, both in terms of toxicity and in terms of their fate, have a lot to do with the dynamic processes taking place on the surface of particles, whether that's dissolution of the actual metals or metal oxides in the particle, which is a fairly slow process, or whether it's a ligand exchange, which, depending on the ligands and the surface, can actually be a fairly fast process. These can often explain a lot of what people are seeing. And this is one of the reasons why, although it can be overwhelming to think about having to test every potentially new nanoparticle size, shape, and ligand coding, I think that using our basic knowledge and what we already know about toxicology and what we already know about chemistry, we can get better at designing smarter nanomaterials. And when I think of green chemistry, I really think of this, of doing things in a smarter fashion based on what we already know. I think one of the classic examples, so these are modes for cellular uptake of nanoparticles, and I think one of the classic examples is one of the ways that nanoparticles are toxic is perforation. So they disrupt the membrane. And this shouldn't come as too much of a surprise because if you coat things with positive charge, so positively charged surfactants, they're going to act just like other positively charged surfactants in the environment and disrupt cell membranes. So if you can look in the literature, and Jim Hutchin has shown this along with a number of others, that when you coat small particles, regardless of what's on the inside of them, you actually get a perforation of the cells, and they end up being much more toxic than the anionically coated particles or the neutrally coated particles. So I think we can learn a lot by just understanding the basic mechanism. As John Warner would say, the mechanistic toxicology can really give us hints into what the final design should be. So with that as a background, it kind of puts us in this situation where we're thinking about how do we work together so that we can design these things in a truly greener way. So as I transition into the part of my talk where I give you the new science, I like to let people know that this isn't something that can be done necessarily alone, because it takes expertise from around campus in our case, but from around various disciplines. So what you see here is really, this is the role for chemists. We're here. We make greener materials, and we choose the methods that we use to get there. I work with partners in environmental science and toxicology to kind of evaluate my progress. How well am I doing? I'm not necessarily going to become a toxicologist, but I can learn from them, and they can help evaluate my choices up here. And it's also important to think about what are the new opportunities? What are the big needs? And the folks that look at those big picture are in policy, they're in public health, they're in business. They can help identify which materials I should be making greener, where the biggest payoffs are. So this is how we organize ourselves here at UC Berkeley. Like I said, I sit over here in the College of Chemistry and focus on actually making the new stuff. And I also work over in environmental engineering and try to think about how it's going to scale up or where it's going to end up, how it's going to affect the large-scale processes that they develop. And then we also work with the Haas School of Business and the Labor Occupational Health and the School of Public Health and Toxicology and Natural Resources. So today I'm going to give you 3 examples, and they come from different parts of that graph. And the first thing I'm going to tell you about is the synthesis of some interestingly shaped nanocrystals, in this case made out of silver, and then how they can be applied and how they were designed such that they could be applied to environmental sensing and environmental remediation of arsenic, environmental sensing in particular of arsenic, and then finally talk about a different class of nanomaterials, so actually some of them that can be used for energy generation, cadmium selenide type materials, and how, depending on what you put on their surface, will depend on where they end up in the environment. Let's go ahead and get started with the first example, and that is the development of this arsenic detector. So this comes to the first part of sustainability, which is meeting the needs of the present. And we want to make sure we do this in a way that doesn't compromise the needs of the future. But you can see there is a present need for arsenic sensing so that you can do effective arsenic remediation. Elevated levels of arsenic actually affect over 30 million people, and one of the big barriers to being able to remediate the arsenic is actually being able to sense it in the field. So as part of my graduate work, I did a lot of research developing surface-enhanced Raman spectroscopy as a way to sense things in water. So the reason why it's a really good sensor for things in water is that water doesn't absorb in the visible part of the spectrum, and we use visible light to excite a molecule in the water, the vibrational, and the difference between the excitation that we give it and how it relaxes is a vibrational mode of that molecule, so you get a fingerprint for the molecule that's in your water sample. The problem with Raman for things like trace detection of metals is that this only happens in 1 out of every 100 million photons. So it's not very efficient if you just shine light in water and look for the Raman signal. If you do surface-enhanced Raman spectroscopy, what you actually see is that the silver particles create a localized intense field. So the oscillation of electrons at this interface between the silver particle and the outside water or other dielectric environment creates a field enhancement. And this field enhancement makes it look to this arsenic like you're shining a whole lot more light than you actually are. And in fact, typical enhancement factors are around 10 to the 6th, 10 to the 8th. So make up for this loss that you get in Raman scattering being a very inefficient way of sensing things. So what you see is you can get typical detection limits using surface-enhanced Raman spectroscopy that are down in the parts per billion range. So there's 2 features, and green chemistry and greener nanoscience is all about design. So what are the things you want to design for in order to make a good SIRS substrate? The first thing you want to design for is sharp corners. So you get a concentration of field lines anywhere where you have a high radius of curvature. Second thing you want to look for are actually junctions. And I'll show you 2 examples, one of junctions between particles, and the second one actually where you can have junctions on a single particle that provide, these gaps, again, provide a much higher enhancement of the field because of the narrow radius of curvature and the ability to communicate between the 2 particles. In fact, Naomi Halis has done a lot of great work on this, including some of the stuff I've cited here, but really showing that this can be thought of in a similar way to molecular orbital theory, which is a lot of fun. So here's how we do it. This is the synthesis that we use, and it's a pretty simple synthesis where we take silver nitrate, and in the presence of this, which is polyvinyl pyrrolidone, which is actually a safe and non-toxic polymeric capping agent, used to be used as an additive in blood transfusions. So we don't have too many toxicity concerns there in a solvent, pentane diol, that actually serves as both the solvent and the reducing agent for this reaction. And to control the size and shape, you basically just increase the reaction time, and this is about 10 minutes up to about 90 minutes. And at any point, you can quench the reaction, take it off the heat, and isolate pure nanoparticles. So if you take a look at the synthesis, there's things that are good and there's things that are bad. One-pot synthesis, you don't need purification or not very much purification as long as everything's working well. It does have elevated temperatures, which might be a concern from a little bit of a process safety and a little bit of an energy consumption standpoint, but they're moderate. The capping agents, so the things that we're putting in, are non-toxic from a human perspective. The silver has some environmental concerns, but they're pretty mild, and from a human health perspective, these things are very safe. And then when you take a look at our E-factor, like I put out there before, we're actually doing not amazing, but pretty well for a nanoparticle synthesis. So for every run that we do, I get about 500 milligrams or half a gram of nanoparticles out for, you know, a few milliliters of pentane diol waste and some other side products. So there's still room for improvement, but it's a good start. In terms of its actual functioning, in terms of how well these particles work at doing what we want them to do, which is interact with light so that we can sense arsenic, you see that they have field-dependent UV vis and dark field properties, which is what we're going to be able to use to maximize our surge signal. And the way that we get those junctions, which is the second part that I said we need in order to create a good sensor, we actually use a very simple, low-cost, low-technology method of fabricating large area films of these silver nanoparticles. So you float them on the surface of water, and this is a Teflon container that you can then compress. And as you compress, this is the compression curve. So this is the area of the container. You can see as it gets smaller, the surface tension starts increasing, or surface pressure, excuse me, starts increasing pretty rapidly, and you actually basically go through what you can think of this as a pseudo-gas phase, pseudo-liquid, and then almost solid phase. And you can see crystalline domains where you actually have very close packing and hexagonal ordering over these domains. So you have very good junctions between the tips of the particles and the edges of the ones next to it. So this is a fun way of creating nanoparticle films that we can then use for surface-enhanced spectroscopy. So here is the setup. You can take a simple green laser, a drop of water, so it uses very low sample volumes, which can be benefit for doing things like medical monitoring. For environmental monitoring, you can just take untreated groundwater, put it on top of the nanoparticles, which can be on a glass slide or any other solid surface. You shine the laser, hook it up to the Raman detector, and what you're able to see is not only a significant peak for arsenic, but you can actually differentiate between arsenic 3 and arsenic 5, the two different commonly occurring forms of arsenic in groundwater. So it's nice because you can actually differentiate what's in there. And you can also do it in the presence of competing ions, so competing phosphate or competing sulfate. You're still able to get this signal from your arsenic. And in fact, when we take a look at what it looks like in as a function of the different particle sizes and shapes, we do see a strong dependence, where if we compare this to just a silver film that we sputter on, which might be a little bit easier, have a lower E-factor, we don't get the actual performance that we're looking for. So but when we do use the octahedra, which were the ones that I showed you that had the triangular tops and were in the film on the previous slide, you can see that even in real groundwater, so this is, or actually next one's real groundwater, but we get a linear concentration dependence over 3 orders of magnitude and can sense arsenic at part per billion level. And in fact, this is possible in both real groundwater and model groundwater. So the next thing that I'll tell you about is how we used a little bit of green chemistry and a green improvement to do even better than that. So that was good. We were able to sense arsenic at parts per billion levels in real groundwater. And then what we wanted to do was see if we could dematerialize, use fewer particles to get the same sort of signal and really maximize the interaction between the light and the particles at the surface. So one of the things we thought about is what if we could, these are pretty large, what if we could etch down specifically on single crystallographic planes to make new shapes of particles. So I found this recipe in the literature. It was reported in 1962, and it was a way to selectively etch on the 111 pits of a 100 crystal face of silver. And so it looked interesting. The only problem from a green chemistry perspective was really this chromic acid. But I went ahead and I took a shot, and what we saw was if I used exactly the recipe that was reported, I basically reversed the growth process, which makes sense because you go from a 111 capped octahedra to a 100 capped cube. You are doing selective etching. You can see how these two shapes are related down here. The next question was, well, why am I using each of these things? And when you take a look at what the delta G driving forces are for the etching reaction in each case, I noticed that it didn't make a lot of sense necessarily that the chromic acid was in there. So I removed the chromic acid, and what was surprising to me and a beneficial result was actually that the etching was improved. So now we could still selectively etch in the 111 direction, but we did so in a way that you actually left more of the face open. And that allowed us to make these new shaped particles, which actually have multiple arms on a single particle starting from these octahedra. And in fact, to make sure that this was in fact selective etching, you could take a look at starting from each of these different shapes, because I could make each of them. And this is what you'd expect if you etched along the 100 faces, and this is in fact what we get in each case. And the other thing that is interesting is if you take a look at the distance in this direction compared to the distance in the 100 direction, you can actually see it change as a function of the amount of etchant. And in this case, it's just ammonium hydroxide and hydrogen peroxide that we're using. So reactive certainly, but not too concerning from a toxicity standpoint, especially now that we've gotten rid of the chromic acid. So this was a greener way of getting to an interesting new particle. And of course, the reason why we wanted to do this was to improve the sensing. And so we see here that, in fact, the sensing is improved. So our best sensing before came from the octahedra. So these are kind of the control here. And what we see now is that when you look at the mildly etched particles, so those are the ones that are right here in the middle, you have these trenches that are just a few nanometers wide. And then the octopod, so this is when those trenches are really grown into gaps of more like 10 to 20 nanometers. You see that depending on wavelength, you get different properties, which isn't surprising because the colors of these solutions change. But in fact, the ones with the narrowest gaps, so those mildly etched particles, which we can control the gap size with the amount of etchant we use, actually work the best. So we get both an advantage in the greenness of the technique and additionally in the performance of the technique by using this synthesis method. And in fact, just as a proof of concept that does fit with the dematerialization notion, we wanted to see if we could actually, instead of using a whole film where the junctions were between particles, could we do single particle sensing? So in this case, we were sensing benzene thiol, which I had coated each of these particles with. And what you see down here in the lower right is actually a mapping. So this is an intensity mapping of this peak, right, which is the actual breathing mode for the benzene thiol on each of these particles. So you can see that even in these closely spaced particles, and this is an overlay of the SEM with the optical or the image, the Raman intensity image, that you can see that even on these separated particles, you don't have anything in between, but you get a peak right on top of each of those particles. We can't show that it's right at the junction because the optical resolution is much, much larger than the few nanometer gaps that are on these particles, but it's pretty cool that we can actually do single particle surface enhanced Raman spectroscopy with these solution-made particles. So I think I alluded to all this as I was going. What makes this green chemistry or greeno nanoscience? You know, it represents a continual improvement in our process, that we try to use the safest starting materials, use things like self-assembly, which are low energy, low cost to build it up, and they use materials as efficiently as possible, lower those very large E factors for nanoscience. So on to the last part of my talk, and that is the end of life. So everything I've told you about so far is taking a look at silver particles, and now I want to tell you about the design principles that can go into making cadmium selenide particles. So when I think about environmental fate, and when I teach about environmental fate, the first thing I do is introduce the environmental compartment. As a chemist, or even as an environmental scientist to a certain degree, this is really as complex as I need to get. I need to think about air, water, biota, the little fish swimming around, the sediment, and the soil. And really, if I think about what properties dictate where it'll end up, it's pretty interesting how nanoparticles fit in. So given the size of nanoparticles and their very high molecular weights, you don't need to really worry so much about vapor pressure, although aerosols are a big concern in this area. You're really thinking about, instead of the air-water boundary, you're thinking about the water-soil or water stability of a lot of these things. So the amount of time that they're going to stick around in the environment has to do with this sort of exchange. And a lot of it really has to do with their stability in water. So one of the things I was interested in doing was characterizing the transport and the water solubility of particles based on their coating and based on their shape and size. So what we see here is the starting palette of this experiment. So if we want to study coating, shape, and size, this is how we started, and that's with 3 different spherical sizes of nanoparticles with narrow size distributions, ranging from 4 nanometers up to 8 nanometers. And then also to throw in a little ringer, we have rods, and those rods are about 3 nanometers in diameter and about 25 nanometers in length. In addition to having these different shapes, they can have each of these different coatings. So basically just varying the chain length of the carbon on the mercapto acids that we used. So in each case, one way to show that we have similar amounts of coating on each of them is to use a zeta potential measurement to measure the surface charge at each of these particles. And what we see, just so this is a way that we can control our variables, is that starting off, regardless of the shape, regardless of the size, and regardless of the capping agent, we're actually able to get the same surface charge on each of these samples. So that means we'll really be looking at the effect of the other differences. We can't just chalk it up to the amount of coating on each of them. So what this is a way of measuring on a short time frame the stability in water. So it's an aggregation rate. How quickly do these come together, crash out of solution, i.e. end up on the soil, as a function of the amount of salt that I add in. So instead of just waiting for them to crash out based on size, I can add various concentrations of salt to the solution, and just like one would salt out proteins or other charged colloids, you can salt out nanoparticles. And what we see is that as a function of their shape and size, you get various stability. So the larger the particles, the less stable they are. Shouldn't come as too much of a surprise. The one thing that was kind of interesting is you take a look at the fairly large but narrow rods are actually much more stable than you might expect at first. But you can take a look at their surface area rather than just their size. So although the hydrodynamic radius of a rod is very large, the surface area is also very large. So if you estimate the surface area, you can see that they actually plot pretty well their stability, their critical coagulation concentration. So that's basically this value right here versus the surface area. You do see that these particles follow a nice trend. So we see that if you want particles that are going to be stable in the environment or stable in an aqueous environment, what you really want to do is maximize surface area. You can either do that through dendritic structures, or you can do that by making them very small. So the second and somewhat more interesting or more important result of this work is really what's the effect of the different chain lengths. And when you take a look at these different length surfactants from 3 carbons up to 10 carbons, you see that you actually get a really significant dependence in their aggregation rate, their critical coagulation concentration. And this can be explained, you'll see in a second, by the fact that the exchange rate of these ligands on the surface is actually much, much faster for the small ligands. So small charged ligands that don't have a lot of stabilization for van der Waals force is leading to much quicker degradation and much quicker exchange on the surface. And this is important because even in the case of the long chain ones, you do get some exchange on the surface. In fact, more recent studies, we've been looking at polymeric multidentate ligands to characterize how quickly and what sort of rates they come off the surface. So to test this hypothesis, you see that if you add excess ligand, so you drive it using equilibrium so that there's more on the surface, you can in fact make them more stable. This is relevant for things like natural organic matter that might be found in waterways and other environmental compartments. And that's another area of ongoing research. So I want to make sure to leave some time, and I think the take-home message, or a lot of time for questions, and the take-home message here is really that this is about thinking about end of life and designing safer materials, recognizing that if we use that nanoparticles are really made up of their constituent molecular parts, and if you're using things that are dangerous for their constituent molecular parts, they're going to potentially have that danger out in the environment. And additionally, if you want them to be stable in the environment, it's all about high surface area and well-bound ligands, whereas if you're using small molecular capping agents or using relatively large particles, those things are going to go right onto the soil. And it may still degrade over time, but you now know where they're going to end up. So that just leaves me to thank both my graduate advisors and my postdoc advisors, along with collaborators, and then my collaborators here at the Berkeley Center for Green Chemistry as well. So now I'm happy to turn it over to questions.
Thanks so much, Marty. We have a question right off the bat, which is what percent of the nanoscience field would you estimate incorporates green chemistry principles? Is it growing?
I think that I'm comfortable saying it's growing. It's certainly growing from the hard work of folks like Jim Hutchinson and Julie Zimmerman and some other labs around the country. And I'd like to think that we're playing a small role in that. What I would say is that if you look at funding for understanding the full impact of nanoscience, There is some as part of the National Nanoscience Initiative. It's much smaller than the more traditional route to nanoscience, but I've been going to the ACS conferences and seeing more and more talk. So I would say I don't know what the overall percentage is, maybe 10%, but growing.
Okay, thank you. Do you have any other questions for Marty? Oh. Sometimes, here we go, we have a hand up. We need you, if your hand is up, to type your question into the question box, because we're not unmuting anyone, and we definitely want to answer your question. So if you can just type it into the question box, we'll take it up right away. So while we're waiting for that to happen, maybe you can tell us a little bit more about the Berkeley Center for Green Chemistry and what kinds of work that you're doing. Is it all the kind of lab work that you've described here, or are there other aspects? Do they do policy? What's the nature of their work with the School of Public Health, for example, and the occupational health and safety partners?
Folks, yeah, excellent question. So being at a center like this is a lot of fun. A lot of our most interdisciplinary successes have been around education. So we have new graduate curriculum for students from all those departments that introduce them to the basics of green chemistry, along with introduce the chemists to the basics of chemical regulation, chemical safety, and some of the traditionally missing components from a traditional chemistry curriculum. In terms of research, it's one of the really important things to realize is public health research, which we do here as well, looks different. It's not necessarily in the lab. It's using large data sets of exposures to do things like epidemiology, or taking a look at finding. And one of the cool projects we have going on now is, instead of waiting for a chemical to cause some adverse outcome, something like breast cancer, what are the molecular markers? So this is working on expanding that understanding of molecular toxicology with the toxicology department in public health to identify early markers of chemical exposure so that you can avoid the adverse outcome. Like I said, this project was looking at breast cancer, but we have other folks on campus looking at other endpoints. I work with the toxicology people directly, both on studying new nanoparticle types, but also on other things like creating safer dispersants for oil spilled in marine environments. And right alongside the toxicologist testing out some of my intermediates and testing out my final products, this is something we actually want to eventually put into the environment someday. So in places where it makes sense, we have laboratory research that matches up, similar to what I showed today. And in other places, it's outreach and more social science type research. Our business school folks actually characterize and publish about what the drivers and barriers are to the adoption of green chemistry.
Thank you. I find that's a particularly interesting aspect of this work to me, actually. But we have another question now. Do you see an eventual use of biomimetics and green chemistry as a more effective mode of creating products?
Yeah, and I think that always looking towards and understanding how nature takes into account processes and does things is a great way to do it. I think nature has many, many good models for us. But it's important to be careful with not only the models we take from nature, both because they're not necessarily always more efficient or necessarily more safe. Rather, we look at how it's done and we still hold the high bar to make sure that's where the green chemistry part comes in, and make sure that we are doing things in the most safe and the most efficient way possible. Sometimes I think about the example of photosynthesis. I mean, trees are beautiful things that produce so many things, like an ecosystem and shade and beauty. But when you look at photosynthesis, they're 0.3, 0.4% efficient. So we're already much more efficient than nature photosystem 1 and 2. So I don't necessarily want to mimic that exactly, although the notion of being able to fully recycle all the material that goes into the tree, I would like to adopt for our inorganic-based solar cells. Keep the high efficiency, but incorporate the notion of complete recyclability reclamation.
Great, thank you. I have another question. Are there any knowledge gaps identified in the nanoparticles' interaction with the environment?
Oh, there's certainly knowledge gaps. I would say that right now, if you were to look at the nanomaterials that are being commercialized and what their potential effects could be on the environment, the biggest gap is in the actual exposure piece, how much of this stuff is getting out of the product into the environment. So you need to know what those concentrations are to figure out what the impacts would be. And the other big gap is the fact that these particles aren't necessarily pure. They're not exactly what people always claim they are. So I think there's a big knowledge gap in what the materials actually are that are making it out into the environment. So those two areas are probably the areas that need to be addressed first in terms of knowledge gaps.
I think that's a subject of great interest to all of us. I have another question here, which is, can you elaborate a bit on the nanoparticle transformation in environment, not only chemical, physical aggregation, but even more so interaction with macro molecules and biological transformation?
Yes, and this is a particular concern with some of the silver particles, so research more related to the first half of my talk. There's a great article that I actually recently wrote a little news blurb about that was published out of Duke, all about the fate of silver nanoparticles in the environment. And they actually did a really interesting study where they sprayed nanoparticles over a controlled, basically, environment in a box. So they weren't exposing real environment, but then they traced where the silver ended up. And what they saw first was that the silver rapidly became silver sulfide and then transferred both into plants. So the plants and animals in those mesocosms had significant levels of silver in them. They didn't yet characterize exactly what form they were in. So you're seeing the components. So what I showed was the first step. So the first step is it aggregates, the ligands come off, and then you can start dissolving. This is why we need to know how much is getting out there, because as it changes form, goes from silver to silver sulfide, it actually becomes more stable, but it can also become a reservoir for silver that can slowly leach over time. And then it's getting into the animals and the plants and what levels and what harm is it causing. Again, that's the exposure piece I alluded to earlier, are big open questions that need to be answered.
Thank you. We're getting a lot of questions now, so I'm going to try to get when zeta differs between nanoparticles, what impact does zeta potential on, I guess it should be, have on persistence in the environment?
Yeah, so zeta potential is measure of the surface charge, and it works, at least what we saw was that it's working very similar to your traditional charged colloid models. So the more zeta potential you have, so the more negative it is if you're using a negatively charged particle, or more positive if you're using a positively charged particle, with the reservations I mentioned earlier about positively charged particles, they're going to be more stable. So if you control for size, control for shape, so they have the same surface area, the larger the charge, the more stable for things that are charge stabilized. Now the big question mark comes in with polymeric stabilization, and this is why that's what we're studying next. When you take and put a very large polymer on the surface, something like PVP, which I mentioned earlier in my talk, but also a lot of other polymer stabilizing agents that aren't charged out there, when you put them on there, they shouldn't have much of a zeta potential. So their ability to stabilize particles is actually functioning differently. sometimes they're much less stable and it still follows the same trend, but that's not universally true, especially for small particles. And since those are some of the safest capping agents to use, I think this is an area that we need to do more research and really understand what those connections are.
I have 2 more questions. I'm going to whiz through them. The next one is, could you give us your perspective on the future of nanopesticides?
I'll answer that one quickly because I don't have too much perspective. I think a lot of what people talk about with nanopesticides, it's really a mechanism for delivery so that you have, you can deliver less pesticide at any given time, and then it's slowly released from the nanoparticle housing, which when you can decrease the loads, I think that's a good thing, as long as you don't have other impacts. I don't know how that field is going, though.
Okay, thank you. That's a really interesting question. So the last question is assessment of natural proteins to integrate mimic into polymers considered green chemistry under your framework?
And so what I always like to point out is I wouldn't call any particular nanoparticle or any particular chemical green. It's always greener. So I would say compared to what? I think that protein mimics can be greener if they're safer and more efficient than whatever they're replacing. So it's all about having that 0 point, that control that you're comparing to. I don't think there's any particular class of compounds that's in green chemistry or out of green chemistry. It's all about thinking about safety and efficiency and ensuring that whatever steps you're taking in your own research, even while you're never going to be perfect, you're thinking about maximizing safety and efficiency.